Assalamualaikum and hi everyone. We are from group number 4. We'll present to you about the Euler's theorem for axially loaded column 1 and fixed and other frees to enhance understanding of the theories and concept of the Euler theorem for axially loaded column. Okay, for the agenda of this presentation is group introduction, objective, formula, example, and the last is conclusion. Okay, we are from group number 4. Also have four numbers of members. Number 1 is Fazli, second Hasbi, third is myself, and last fourth is Lokman. Okay, for the objective of this presentation, this topic start with the behavior of column, generally discuss of bucking and determination of the axial load needed to buck, follow the Euler theory and the calculation with the different type of support in the column. Okay, next for the introduction. Euler's theorem, also known as Euler's bucking formula or Euler's column formula, is a fundamental concept in structural engineering that predict the critical bucking load and the axially loaded slender column. Okay, the assumption of the theory. Okay, number 1 is the column is perfectly straight, and number 2 is failure of the column occur the bucking only. Number 3 is the compressing force act on the center of the section. Number 4, the column behave elastically. Number 5, the column material is homogeneous, and the last is the cross section of the column is uniform.
Thank you very much for my fellow member Shamil. Now I am going to explain about axially loaded column. An axially loaded column refers to structural member that experience an axial or compressive load along its central axis. The load is applied parallel to the axis of the column, causing it to undergo deformation primarily in the form of buckling rather than lateral bending. So I will hand over my for the next slide to my another member. Thank you.
Okay, I will explain about the formula. The formula is PCR equal to pi square EI divided by L square. PCR means the critical buckling load, which represent the maximum compressive load the column can sustain before buckling occurs. E is the modulus of elasticity of the column material, which describes its stiffness. I is the moment of inertia of the column's cross-sectional area about its natural axis, which measures its resistance bending. L is the effective length of the column, which represent the unsupported length between the columns and support. Okay, next I will explain about the effective length of column. What is effective length of column? The distance between two consecutive places of contraflexure on the column is known as the equivalent or effective length. The location on the column where the direction of the column's axis changes is known as the point of contraflexure. By the idea of an effective length, the critical loads for columns with varied support conditions may be connected to the critical load of plane and column. Okay, this is example of effective length of column. And the next slide, Fazli will explain about fixed and free ends.
Okay, thank you, Lokman. Okay, my name is Fazli. I want to continue about effective length of column. For our topic today is fixed and free ends. Okay. So we can see this slide. We assume that this is identical to the pin end column with length of 2L. Likewise, the solution of the problem is identical to the solution of pin end and effective length of 2L. Using of concept of effective length, Euler equation becomes PCR equal to pi power of 2 EI divided by 4 L power of 2. Okay, for this condition have two conditions. There is fixed ends and free end. Okay. For first condition, in this case of fixed end, the column is considered to be fully restrained against the lateral displacement. This means that the column cannot rotate or deflect at the end. The effective length of column with fixed end is equal to the actual length of column. Okay, for the second condition, when the end of the column are free, they are able to rotate and deflect. In this case, the effective length of typical list then typical less than the actual length of the column. The effective length factor depends on the ratio of column actual length to the less radius of gyration. Okay, let's go to see the example of the calculation. This example consider a universal column 200 mm times 200 mm with flake thickness of 10 mm and web thickness is 7 mm. The height of column which is fixed in concrete at its base is 10 meter and the load is applied on the top, free joint. Calculate the load necessary to induce the column to buckle. Okay, info given B equal to 200 mm. B is for flat length. Okay, TF 10 mm. TF for flat thickness. D 180 mm. D for the web length. TW for web thickness 7 mm. L for the length of column 10 mm. E for young modulus of the structure 210 GPa. Okay, we see this solution. First, we need to calculate moment of inertia using the I equal to 2 times B power of 3 times TF divided by 12, then TF3 divided by A. So we put the amount. So I get 13338478 mm. Okay, then we can then after we get I, so we just put for buckling formula for buckling load, we calculate the P critical load for this column. Okay, just we use our formula PCR equal to pi EI divide for 4L. We insert the amount, then we got P equal to 17.278 kilonewton. Okay, thank you.
I will share to you guys the conclusion that we got from our study. The conclusion of Euler's theorem of column is that for long and slender column, the critical buckling load decrease as the column length increase, and it increase as the column flexural rigidity increase. This implied that shorter and stiffer columns are more resistant to buckling than longer and more flexible columns. It is important to note that Euler's theorem of column assumes certain idealized conditions such as a perfectly straight column, uniform material properties, and no imperfection or eccentricities in the loading. Real-world column may deviate from this idealized condition. An additional factor like lateral bracing, material imperfection, and eccentric loading need to be considered for more accurate prediction of column stability.